So the work of F is the change in value of potential from one endpoint to the other endpoint. And so, you might know about gravitational field or electrical field versus gravitational or electrical potential. And in case you haven't done, any 802 yet, electrical potential is also commonly known as voltage. Okay? It's the one that makes it hurt when you stick your fingers into the socket. Don't try. Okay, and so now conservativeness means no energy can be extracted for free from the field you can't just have a particle moving in that field and going on indefinitely faster and faster, or if there's actually friction, then keep moving. So total energy is conserved. And I guess that's why we call that conservative. Okay. Okay, so let's end with a recap of various equivalent properties. Okay, so the first property that I will have for a vector field is that it's conservative. So to say that a vector field is conservative means that the line integral is 0 along any closed curve. C. Maybe to clarify, sorry. Along all closed curves. Okay? Every closed curve that you give me any closed curve, I get 0. So now I claim this is the same thing as a second property, which is that the line integral of F is path independent. Okay, so that means if I have two paths with the same endpoints, then I will get always the same answer. Why is that equivalent? Well, let's say that I'm path independent. If I'm path independent, then if I take a closed curve, well, it has the same endpoints as just the curve that doesn't move at all. So path independence tells me instead of going all around, I could just stay where I am, and then the work would be just 0. So if I'm path independent, then I'm conservative. Conversely, let's say that I'm just conservative, and I want to check path independence. Well, so I have 2 points, and I have 2 paths between them. I want to show that the work is the same. Well, how do I do that? Oops, C1 and C2. Well, I observe that if I do C1 minus C2, I get a closed path. Right? If I go first from here to here and then back along that one, I get a closed path. So if I'm conservative, I should get 0. But if I get 0 on C1 minus C2, it means that the work on C1 and the work on C2 are the same. See, so it's the same. It's just a different way to think about the situation. More things that are equivalent. I have two more things to say. The third one, it's equivalent to f being a gradient field. Okay, so this is equivalent to the third property, f is a gradient field. Why? Well, if we know that it's a gradient field, then we've seen that we get these properties out of a fundamental theorem. Question is, if I have a conservative or path-independent vector field, why is it the gradient of something? Okay, so this way is the fundamental theorem. That way, well, so that actually, let me just say, that will be how we find the potential. So how do we find potential? Well, let's say that I know the value of my potential here. Actually, I get to choose what it is. Remember, in physics, the potential is defined up to adding or subtracting a constant. What matters is only the change in potential. So let's say I know my potential here, and I want to know my potential here. What do? Well, I take my favorite particle, and I move it from here to here, and I look at the work done. And that tells me how much the potential has changed. So that tells me what the potential should be here. And this does not depend on my choice of path because I've assumed that I'm path independent. So that's what we will do on Tuesday. And let me just state a fourth property that's the same. So all that stuff is the same as also 4. If I look at m dx plus n dy is what's called an exact differential. So what that means, an exact differential means it can be put in the form df for some function f. And I'm just reformulating this thing, right? Because I'm saying just I can put it in the form f sub x dx plus f sub y dy, which means my vector field was a gradient field. So these things are really the same. Okay, so after the weekend on Tuesday, we'll actually figure out how to decide whether these things hold or not and how to find the potential.